Hello, welcome to the additional Altium tutorial. Today I just want to go over some things that might have not been covered in the Altium 365 tutorial for the A-stable multi-vibrator circuit. So today, to make it easier to manage Altium projects in a third-party Git repository similar to GitHub, I'm going to be making a project locally and having everything local, including the library. So the first thing we do is go to File, New, and then we open up a new project. And then what we want to do is make sure that's under local projects. Then you give it a name. And I want to make sure this is an empty project first, right? And then the next thing we want to do is just, you can just go over here and see that it's a completely empty project. And then we just do create. And then you see now we have no documents added. So we right click onto this and then we go over here, add to new project. We added schematic and that is used for designing the circuit. Then secondly, we want to add the PCB file, and that is where we're going to do the PCB layout. Awesome. Now the next things you want to do is create a schematic library, because that's where we're going to have pretty much all the schematics that we have for the program. And then the next thing we want to do too, well, let me close that so I don't get interrupted, is to also have a PCB library, and those basically pair up with the schematic library. So now that we have all that done, we can now press save to be ready to go. And you just press save. You can name it whatever you want, and then usually what I do is just stick with one name of what your project is, right? So for this tutorial, we'll be making the SHT41 sensor, similar to the one that you'll be using for the firmware tutorial that Telus is getting for you guys. So now we can press save, right? Press save, and then press save, and now we're all ready. So moving on to the next part. When you design a PCB, a lot of time people forget that PCBs are something that are made in the real world, right? You could ask your neighbor to make something for you, but it might not be the nicest thing. So usually you'd reach out to a manufacturing company to do it. And then the one thing you have to consider is that not everything that's made is perfect. So you have to expect tolerances. And then if you look through here, JLC has all their capabilities listed. This is different across all different PCB companies. This is why you can't make an antenna design or copy an antenna design online or anything with an impedance profile and then use that design and have it produced at different manufacturers and expect the same outcome, just because the different basically layers that they use, the different materials they use, that'll change the characteristics of the traces and the impedance of it, right? And then it'll also change how your antennas will perform when you design them. And as you look through here, we have all the different capabilities that they have. And then, for example, you have over here the vias. And as you see here, we're able to do a via hole as small as 0.15 millimeters and have the diameter be 0.25 millimeters. As you get more and more narrow to one side, the boards JLC has a harder time producing these more reliably. Because imagine if you had a trace basically connecting to the ring over here. A problem with that is that they might accidentally just shift over the drill bit and drill down where the trace is connected. And what that does is basically disconnecting the trace, making your PCB pretty much useless. So it's good to find a nice middle ground. So one of the things that we could do, and I mostly do this out of just being a little bit lazy, is that if you see here, this is something that I've been using for years. And it's been going strong for quite a bit of time. And JLC has only been getting better. So if you're able to design a board around these rules, then pretty much it's going to hit a nice middle ground of not being too narrow in the tolerances and the specs of what JLC is able to provide, right? And then just meeting a nice middle ground. So let's stick to what these design rules have, and we'll be able to make more reliable boards moving forward. So if you see here, we have different options that they offer, and these are pretty much just copied from JLC's website. If you do need much smaller vias than what we have here, you can go with this number here, and you just need to go and compare and then make the changes in the design rules. And there's a lot of different YouTube videos on making custom design rules, and that's sometimes usually needed to do every time you move from manufacturer to manufacturer, just so it's easier to have it all like prompted and all the errors shown directly in the program rather than you having to inspect it with your eye because you might miss it. Right? So if you see here, we have a 2-layer board. Usually I abstain from using 2-layer boards unless it's very necessary and I need to make something that's really cheap and simple. I tend to lead to more 4-layer boards just because you're able to separate your signals with ground, ensuring that they always have a return path. And then 6-layer is good. It comes with a lot of additional features, right? But the one thing you have to expect is that when you go from a 4-layer board to a 6-layer board, the price tends to jump, similar to 2-layer. So JLC offers a 2-layer board at 100 by 100 millimeters for relatively cheap, I believe $2 for 5 boards. Then for 4 layers, it would be 50 by 50 millimeters. But imagine you did 50 by 60, that would be $7 for 5 boards. And then for 6 layers, if you might be spending $20 for 5 boards if you go over 10 millimeters of what their limit is. So it's good to think about like how many boards are you going to be making, how much do you like, how many layers do you want and how much do you want to spend? As well as you have to consider the copper ounces too. So 1 ounce copper is good for low power stuff. 2 ounce copper is for high current stuff or high energy, right? High power. And relatively you can get away usually just with a 1 ounce, even for things that go up to like 600 watts. You just have to be really like creative in the way that you do use the different layers. As well as you have different layer stack ups. So you have to also consider is like you want 2 layers, right? And then you have the different thicknesses. Lower thicknesses can sometimes provide better noise results, right? As it's able to have closer references, and then it decreases the amount of fringe fields that you have affecting other signals, right? And then you can also go with thicker PCBs as well. So you have to think about the actual like thickness and how that works out, because if you have something that's 0.4 millimeters, you're going to be able to twist it into a donut relatively easily, right? Compared to if you had something that was 2 millimeters, that thing will have to snap if you're going to bend it. And then you also see here that the 4-layer boards have the same options, but they now have numbers next to them. And this is basically like a impedance profile. And if you're doing any type of differential pairing where you need to basically path a trace or lay down a trace at a very specific impedance, or you have to match impedances between 2 traces similar to for differential pairs, then you're able to basically get a guarantee from the manufacturer that if you use this setup and then you basically implement it into your program and you let the program do the math, that he'll be able to make everything around those impedances by like a variance of like 10 to 15% off, right? So you can make sure that when you go to JLC, you design an antenna, and then when they make that antenna, they're basically going to produce something that's relatively what you want, compared to if you just went with a random 2-layer board with the same antenna design. It's not going to work just because the impedance will be different. It might work, but it might be really awful. And then you have different impedance profiles, and that'll change the math and the thickness of the traces, right? And I usually just go with this one. It's relatively well, but you can play around and see how they affect the different boards, right? Moving forward, in this tutorial, we won't do any impedance matching, but there's a lot of tutorials on it. So if you ever do need to design your own antennas, or if you ever need to do differential pairs, it's easy to look up. So what you can do is just go over here to code and then download, and then you'll be able to get that. And then you can add that directly to your Altium file, mostly the PCB file. So now that we have the PCB file open, the first thing we want to do is to get ready for this project is that we want to go over here. We went to design rules, and then we go over here, we right click, and then we do import rules, right? And then we do Control A, select everything. We can go to downloads, and then I can find what I downloaded before. And then the first thing we'll do is we'll find design rules. And because I said I'm going to go with a 4-layer 1 ounce board, 1 ounce boards are a lot cheaper than 2 ounces, and we'll go forward with that. And then I can do like OK. And that sets that. And now the next thing that we want to do is the layer stack manager. As you see, we only have a top layer and a bottom layer. And if you want to be able to have more layers, we basically have to change the layer stack manager. And the nice thing about having all these profiles already set up for you is that you're able to start a 4-layer board without having to type in or add different layers here and having to type in all their thicknesses and their ounces and all their coefficients, right? And it makes it easier too. When you look over here, you're able to add impedance profiles, right? And then that'll basically be able to calculate the trace gap, the trace widths, and all of that for you for a specific impedance based off of your stack up. So it makes things a lot easier for you, as well as you have different types of via types too. If you ever want to explore like micro vias or vias that go only partway through the board. All right, so let's just go ahead, and then what we can do is we can load the stack up from the file, right? And then we can go downloads, and then we can go here again, and then we can go stack ups. And because I said we're using 4-layer 1 ounce, I usually go with 1.6 millimeters because that's a standard thickness, and it's relatively cheap compared to if you go to a more narrower board, it can become more expensive. So this is a good all-rounder. Even though we're using an impedance profile like layout, we can just pick a generic 4-layer board for what we're choosing, right? And the price doesn't change if you choose to make it impedance match or not, right? So it's all good in that aspect. So now we can just save that. So this is all ready. And if you see now, we now have a top layer, a mid layer, another mid layer, and then a bottom layer. And what I'm going to do is basically route power, because voltage, all the energy basically goes along the trace, right? And there's mostly signals you have to worry about. But then if we make the middle layer here ground, and we make the next middle layer ground, and then bottom layer another signal / power, then those will be separated by their own ground plane, so you won't have any fringe fields affecting each other. The only thing that you would have to worry about is any fringe fields that are basically coming off traces that when you go from the top layer with vias to the bottom layer. And I can kind of show you an example on how to mitigate that. Okay, awesome. Okay, starting off the next part. I am recovering from a cold, so I'm going to need to have a bunch of little breaks, but hopefully we get through this relatively well. So the thing that we're going to be designing is the SHT41. The R3 basically means that it has this filter on the top, a membrane, and this is the same chip or IC that you'll be using for the firmware tutorial that already comes on those little dev modules that you'll be getting. So one thing about this is that whenever you design anything with PCBs or electronics, is that a lot of data sheets, sometimes for some components, like for this one, it's relatively small, it's really easy, and then there's some things that you want to quickly look through. So electrical specifications is always important, so you're able to know exactly how much your supply voltage is, right, as well as the amount of different currents that will be going through the PCB, so you know that you're able to supply it with the proper power source, right, as well as the max voltage if you're going to implement any type of safeties. Usually datasheets have a very similar format or between the different companies. So usually you have electrical properties, what you just saw earlier, and then you would have firmware kind of in the middle. And then you'll basically, over time, you'll see different calculations. And if you keep scrolling down, towards the end, you usually get the physical package and how the format should be. It's always good to go and look at this and look at the suggested LAN pattern / pad to see what sizes they use. And that's something that you always want to verify, just because a lot of time when you pull a pad online, it might be incorrect, and then that'll mess up your whole design. And then you can just keep scrolling. It's good to just do a quick, scroll through. And then you have the way that it's packaged. This doesn't really matter to us because we're doing a small scale assembly. We're not doing large scale assembly. So this is basically like a gigantic wheel that feeds it into a pick and place machine. And that just improves manufacturability. And then usually towards the end of the datasheet, you have nomenclature. And that just tells you what all the different letters mean and all the different positions. Right, and you can see here, the 2 and the 3 at the end basically shows you how many, if you get a reel in it with 1,000 pieces, it'll end with a 3, so you can tell what you're buying relatively easily, right? And then it even goes through here with ordering information, so they kind of go a little bit in depth with that. But as you scroll through the data sheet, the most important thing you want to do is basically look at reference designs, because sometimes for things that are hundreds of pages long, you might lose interest if you think you have to read through every little part. So it's always good to look online, see what other people are doing, see what data sheets are. Like the entire NRF kits that you will be getting have all their files accessible on Altium. So it's really easy to see what they're doing and copy what they're doing because you know that it works. They're selling it, it's successful. And then the one thing that's nice about this chip today is that it's relatively easy. It uses I2C. I would recommend looking it up and understanding what the pull-up resistors are for, right? And it has 2 pull-up resistors for 10K, right? And that basically it has the whole concept of an RC circuit. And then if you have resistors that are too large, then your square wave will be too phase shifted or might not go to a high enough voltage in time, and then the signal wouldn't be picked up compared to if you made it too small, then it would just be a short from 10 volts to the signal, and then that would mean that you basically wouldn't be able to have any type of control on the line because you have nothing pulling it up. And then you have, of course, a decoupling capacitor, and that's to make sure you reduce your loop inductance to the IC, and you relatively want to keep this close to the VDD pin as much as you can, right? As close as possible. And if you put it back on the other side of the board, that's when you have to consider the thickness of the board, right? Because it could be either if you have a 1.6 millimeter board that's like a 1.6 millimeter thickness board, right? If you have the capacitor on the other side, you have to account for that thickness as well as how far it is away compared to if you had on the same size, right? Then you might be able to, on the same side, then you might be able to make it pretty much be a lot closer, and then that'll give better or more reduced loop inductance, right? And that's ideal. So when you're looking at this IC, as we scroll through the data sheet, you'll notice that there isn't really an idea of like telling you how is this thing placed. So you might just slap it down on a PCB, right? And if you didn't do your research, for example, like imagine for I say, it's always good to look at different designs. You'll see here that this has like a little cutout in the PCB here, and you can kind of look at what they're doing. They have the little pins in the headers, right? They have a capacitor here. That's probably the one that we saw there, right? They have some pull-up resistors here. They have something over here. I wouldn't know what that is for right away. But then you have like this little device here because they have a VN and a 3V0. So it's like, oh, that might be like basically a down translation of voltage from an LDO. And here are basically the filtering capacitors for the input and the output. So it's good to kind of understand why do they do this. So you might go and look through the data sheet and be like, why is there a gap here? Why did they do that? Right? And you might go through basically here. You might scroll through it and you'll never find an answer on why they did it. And then you might go through here and then you'll look through every single page and you'll find out, oh, there's nothing about it. It's like, why did this random example here? And a lot of these dev boards have this gap here. And then if you're lucky enough, you can do enough research or you get lucky, you might come across a data sheet like this where it tells you that like a lot of components on a PCB are a constant source of heat. That heat might migrate and basically affect the readings of the humidity and temperature sensor here, right? So it's good to consider like maybe having this kind of, what this does is very similar to a thermal relief where you're able to increase the thermal resistance of this area of the PCB by making this gap small. And you'll understand what I mean by thermal reliefs when we put down the polygon pour. Right, so that's something that you have to consider too, right? It's always good if you just went the data sheet and just copied exactly what it showed you from here, and you didn't even think about the actual design and how it's placed mechanically, then you'd miss this entirely. So it's always good to kind of pick up on that and see what you can do, as well as like for more complicated chips, they usually always companies want you to use their chip. So they'll always give you usually a reference design or an easy pickup or somewhere at least, because they want people to be adopting these chips and they want them to be using it because that's how they make money. So let's go back and let's go ahead and implement this IC. As you see, we have the 2 pull-up resistors as well as the capacitor, the sensor itself, and then obviously we need a way to actually plug in with the sensor, similar to how you see over here. We probably just need to find one of these headers as well. right? We don't need as many pins just because we don't have the LDO to allow us for it to put a 5-volt. Dev kits do come with a 3.3, not 3.3, but a 3.0, unless they change for the latest ones. But pretty much that's all we need. So Altium is really nice that it has a manufacturer part search. And what we can do is that we can take the chip that we'll be trying to use online and we can put it in here and see, like, do they have it available? Is it a model? And if you see here, there's like a chip with a red line through it. That means that the model and the footprint is just not available. So the next best guess would be to look at SnapMagic or SnapEDA, and we can pretty much, you see here, we have the footprint, we have the symbol here, and then we have the 3D model. So we can go ahead and download this, and we choose Altium, of course. And then now we have this folder. You can see I already downloaded before, running through this before, but we can now extract that. And now what we can do is that we can go over to this guy and we can go over here to the PCB library. We can right click on this, copy. Then we go back to projects. We go to our own little tiny libraries here. Right, I copied from the schematic. So now we can just pretty much go here to our own PCB library and we could paste, right? And we can also delete the one that we're not using that was created initially. Next thing we can do now is that we can do the same thing to the actual PCB library. We can just copy this, right? We can go over to ours, right? And then we can just, go open the PCB library, right click and paste one component. And then we can just delete the old one. So one thing they have to always do is just make sure we save. You have the little star here. If you don't save, it won't register or be picked up from one or the other. And it's just good to save all the time, just in case if this program crashes, which it sometimes does if you don't have the most beefiest PC in the world. Right, and now that we saved, we can now go over here and we can browse, and it automatically picked up the model for us, luckily, because it was already linked to something similarly. And then we can see that we have our file path right here. It's picking up in the right place, and it's not picking up where I downloaded it. You can press OK. Now this guy and this are linked together. We can press save. So one thing we can do too is that when you have this open, you have this selected here, right? You can now go over to the right side and you can pretty much add the supplier link and parameters. And then what you can also do is just copy the name here. You can also do it up here. You have a little file that shows up. You can click on that. It'll copy that link. And what you can do now is that you can go over to your schematic library and you can click on this, and now it brings it up and you can edit supplier links. It's always nice when you do these projects to link it to a real world component. So if someone ever comes over to your design, they're able to see what you're actually trying to add. So when they look at the component, they could be like, okay, they wanted this one specifically, right? And then they can look that online and buy it. It makes it a lot easier for everyone when you're sharing a project. So we can add that. And then we're good now. And then now this component is ready to be added. So one thing is that you see here, there's no like reference or any type of designators. We have a designator J. A lot of times designators can mean something. So you have R for resistor, C for capacitor. And then usually what you can do is use U for IC. Sometimes I see J's be used for like headers or whatnot. So depending on how you feel about it, right, there's some, you can look up what the letters mean. Usually what I do is I go to tools, then I go to document options, I believe. Then you can show hidden comments / designator. Sometimes this is a little bit buggy. So if you move it, it might just stay where it was. But then when you save it and you put it down, it'll be good to go. So for here, for the value, you can basically just like write whatever you want. You can write down the chip name entirely. You can just do a simple name, right? Then here we can basically do J, or we can do U question mark for an IC, right? Keep typing the lowercase, and now we're ready for that. And it's nice you're able to see that. So now we can just make sure we have that saved. It's saved. And now we can go over to the schematic library and we can just press place now because it was selected before. And now we're in business. We have the main IC down. Now the nice thing too about GLCs. So imagine if we want to get resistors, right? We could take it from the manufacturer part search. Hopefully, if it actually works out for me. But here, and now what we can do is go to the filter here. If the filter wants to work, it might be giving me a little problem. Here we go. And now what we can do is that, like, whenever you do PCB design, you want to pick something. Usually small package sizes are harder to solder, but they're cheaper. They're better for like pick and place machines. And they're usually relatively cheaper. So it's for more production or more units, it's better. 0805, right, is larger weight, easier to solder, has usually higher power, require capabilities as well as higher voltages, right? And you want to choose something that makes sense to your design, because you want something that isn't too big, because it makes it really hard for any small compact designs. As well as you have to think about different parasitics and like the different types of, like, as a resistor gets longer, you have to consider that there is inductance. That is, there's more inductance for longer resistors, right? And that's something that you have to consider too, right? And if your design's really sensitive to higher frequencies, that's something you have to consider. Luckily for us, a lot of biological systems are relatively low bandwidth, and you can just like low pass filter most of it, any of the noise out. That's the same reason why you can make a lot of 2-layer boards that cross signals work too, because a lot of the signals there are relatively low frequency, and you can kind of just low pass everything. So now we have a resistor. We just want to make sure it's 10K. So for I2C, sometimes you'll see 10K, sometimes you'll see 4.7K. There's YouTube videos on how to size it out, right? And then you can also verify the timing requirements of how the waves are with an oscilloscope. Or if you have an LCR meter, you're able to use that to find out what the bus capacitance is. If you actually look at the data sheet here for the SHT41 and you look up capacitor, the one thing it'll do is bring up table 4. Table 4 talks about the capacitive bus load. So if this is the only thing that you have on your I2C lines, you're not able to use this, right, for fast mode or the standard mode to calculate your pull down resistor or your pull up resistors, right? So that's what I mean about, like, you have an RC constant you have to consider, right? You don't want it too slow, and you don't want it, too small that you don't actually have anything to pull up, right? Because then it's not able to basically control the signal without the pull up. Because what you have is that you have an open drain MOS probably on the MCU side, and what it does is pretty much short the line, and that's how it's able to take the pull-up voltage down to the ground, and that's how it's able to start communication with the slave chip. So one thing that we do now is that we pick a nice resistor that we like. Oops, I accidentally clicked that, and now we can do is that, because I want to keep everything local, I'm just going to download the file, or download the component. Let's go. And then we want to copy this here. And then I'm actually want to start deleting these things. I'll stop fighting it. We can just choose something here. Oh, not in here. But let's save. No, I must have chose this guy a long time ago. Now the components are downloaded. We can go here. Right, and then now what we can do is we find the one that we downloaded today. Now what we can do is that we can just extract all. Right, and then we can just click on here, the int lib, and that basically runs the same thing that we did earlier with snap EDA. Right, and then you know the drill. We go over here, we click up the component. Right, one thing you want to do too is always, like, you can press 3 and 2 to switch between these views. You press Control F to kind of flip it around. Same thing here. If you're going on the back side, you might want to press Control F to flip the design around. It makes it a lot easier for you. But what you can do is go to the third one here, and then you can basically do this Control M, and that makes this blue. And what that does, it lets you do measurements. And you see right here, this is 1.6 millimeters, which is relatively the same length as 0603. So we know that this pad makes a lot of sense. And you can do Shift C to remove any type of annotation. So it works too in the 2D mode. It's really nice. And if you go to your properties, you're able to change the different type of like snapping that you can do. So now you can see like how long is this pad, right? And you can get very specific things. And you can press Q and you see here my dimensions are now changing. Same thing over here. You can see it going back and forth from millimeter to mil, right? Usually it's good to work in millimeters. The schematic is good to, usually what some people do is they work in the schematic in mils, right? Because you want to make sure that everything on your schematic is kind of on the grid. And if you're using a mil grid, then you want to use mil components. Most components are made for a mil grid. All right, and then you can basically design your boards and put the components around each other in millimeters, right? And then you see sometimes people will route traces in mils, and they'll do vias in millimeters. It's kind of really like similar to when you go to the gym and you say pounds instead of kilogram for the plates, right? Unless you do Olympic weightlifting and all that sorts. But you know the drill. We just go over here, we copy the one we want. So we have different options. And you can either take all of them if you really want to, or you can just take the one that we like. And it's like, you see here that you have a pad. You have to think about the physical implication of what going with this pad versus something like this means, right? And a pad like this has a lot more surface area, right? And this is good for like, if you want to put your soldering iron down right here, you're able to touch both of these and heat them up relatively nice. So this is good for like hand reworking. Where something like this, where also some ICs, or not ICs, but SMD components you see might not have the pad come out at all. And it's specifically made for hot air or like surface mount, like basically pick and place and hot air or an oven, right? Just because they know that you wouldn't be touching an iron to this, so there's no space for you to put an iron, right? And it makes it harder to solder because then you have to heat up the pad through the resistor, and that'll cause damage to the resistor. So B is like kind of like a nice little middle ground actually. So I'm going to go with that one. Right. And also if you make the pad too big, if you ever have solder with enough acid / flux on it, right, it'll just float into place. But if you make pads way too big, it'll kind of like flow off the pad and have problems. So that's why you don't ever want to make these too big. And that's why even like the dimensions of the actual width of the pad, right, it matches very closely to the actual like metal contacts on the component, just because it starts becoming like a slip and slide as soon as you start putting, you know, pads are too big. So you don't want to go crazy. You want to do just right or just follow what the manufacturer recommends. So basically I copied this guy. I did that again for like the 20th time, and then you can come over here too and you can just copy this guy too. Right, and now we can just go. It remembers for both. Right, and they can go that there. We can go this here. Right, you can paste that here if the option. What we can do now is just press Control S to save. Sometimes it doesn't work if you're like if you're in the wrong menu or like clicking on the wrong thing at the time. And you see here, like, I turned on the options earlier with the pad to see like the designator and like the resistance, right? And it's like this was down here weirdly, so you can make it like a little bit nicer, right? You can also press like, you can also come here to the properties, right? Or just press G. And if you see here, you have the grid changing. And like I said, I'm working in a millimeter grid. And when I'm placing down, most components are in millimeters for schematics. Or not millimeters, but mils, like thousandths of an inch, right? And then for this one, you can just kind of keep that like this. Actually, we'll leave that there. So then usually what happens is they take the comment for the name for the components if you want to easy upload it, right? And then when we actually place it down, we can rename it to like R, like 10K, just so that it's easier for us. And what you want to do now is that we kind of removed everything else. So I'm just going to delete those. Right, and then for the B, we're going to have it connected to the B. We make sure that the path that it uses, it's the same library that we have in this working library, just so we know it's not pointing towards where I downloaded it. And then when we delete that later on, it doesn't, you know, get fussy and fight you. The same thing, we want to edit the supplier link, right? And then it's just going to take pretty much the comment here, and then this is going to go here, right? And there we go. Now we're in business, right? And now we can go here, and we can just place this guy, right? And we want 2. Sometimes Altium, especially when I have OBS open, it can kind of like fight me a little bit. So it's good to see, is this name is missing. Library not found. So I need to go and fix that later. Or I just need to place more of these guys just because maybe it just didn't like save properly. Right? Yeah, it's mostly has to do. I noticed that Altium is a little bit more cursed when it's when you have OBS open. I've ran into so many bugs making these tutorials than I would want to. But yeah, okay, let me see if you click on that again. Right. And then I click on this, save. Then we come here. We have the schematic down here now, and now we can place. And hopefully, like you see this guy, it has a footprint. And then here, it's just not having it. So we'll have to figure this one out later. And it might just work with itself later on too. But yeah, you probably won't have the same amount of troubles that I'm having right now, right? Just because of Altium, you know, and OBS, I think just like to tough it out. And then now the next thing we want is a 100 nanofarad capacitor, right? And then we can do like I believe it's 100 nanofarads, just also 0.1 microfarad. All right. And then now see 100 nanofarads. And you always want 3 times the voltage, so we're just going to choose that. And oh, I looked that up in components, so let's do manufacturer parts search instead. Now we look at capacitors. All right, we come over here. We can look up 0.1. We're going to do 100 e to -9. So I'll do 0.1 e to -6, right? And I could just type that in. But now we get 100 nanofarads, and then now we want to make sure our capacitor, right? For example, for the resistors, I said, right, or like you want to make sure that you have 3 times the power that you have. Just because if you're running the resistor hot all the time, then its value is going to shift over time as it degrades. Same thing with capacitors, they have a voltage that derates. So the more voltage you apply to it, right, the lower like effective capacitance that you are ideally get out of it for a ceramic capacitor. So it's good to choose something that's like, if you imagine you're doing 3.3 volts, you want 3 times that, so at least a 9, right? And that doesn't account for any transients, so you might want to go a little bit higher too. So maybe like for 3.3 volt system, you want to choose a voltage of like 15 volts, right? This is 25. It's fine for us. I'm just going to go and take this guy, and then we can download it as a file library. Right, and then I can just copy this just in case, so I can find it again later. Right, go over components. Right, more options, and then now we can refresh, see what the latest thing was. Now we can extract all. Then we click on this again. Another instance is running. And then I tried that again, and now we have this again, and you know the drill, right? We just basically take what we want, leave what we don't want. You can take them off if you want to, but I think B is relatively nice because it's a nice middle ground where the pads aren't massive, and it's just right enough for you to have a soldering iron that on the pad right in the corner with the actual metal contact of the capacitor. So I'm just going to copy this one. Copy, and then now we can go over to the schematic one, and you can see that the reference here is hiding. So now we can do is show it in comment, and we can put it move these around a little bit. It's if you want them on the same side, that's good. That looks clean to me, and I'm happy with that. So now what we can do is that we can just copy the B, or not the B, we want to go to the schematic library and we want to copy this instead. And now we go over here. I'll add this one first. So we want to just paste this down. Right. We'll save that. And then now I just want to go over here and paste it here. And then now we have the options that we don't want. We'll just remove those. Yes. And then we'll go over here to description. We'll browse, make sure it's the component that we want. That is it. It's in the right place. You press OK. Then you could basically click on this guy again. I already have it selected, so it's coming up. And now we do edit supplier link, or you can go manufacturer part search first, then add link and parameters. I believe I forgot to do that for the capacitor. We can always just do that for this guy. Right? We have the name and we have the power. So basically, right, we can go over here, back to resistors. We have the specific name. Just basically add supplier link and parameters just in case. It doesn't matter. You can always do it later. I'm pretty sure I already had it. When we click on this, it comes up to, oh, yeah, I made it. Oopsie. By not putting this either. But that's fine. We can just add. I'll use the comment, and then we press OK. Right, and then OK. And now we're in business, and hopefully when we put this guy down, it doesn't fight us like the resistor does. Right, this guy is good. This guy's footprint is missing. And things do happen. Things sometimes have problems. That's normal. Software is not the best that it used to be. But we can, maybe what I can do here is just say goodbye to this resistor. If it's not being good, I can try maybe relinking this, change it from here, this one, right, and change it back over to this one. That's okay. We can try saving that now. Right, we don't want to try too hard. If it's not working out, it's a resistor. We can find another one. There's more fish in the ocean. Not in that sense, but in the component ocean, there is definitely a million resistors. We have infinite selection. Right, and then let's see if we can place this here. And let's see if that gives us the footprint. It's loading. Right, and one of the ways you can to see if it's actually linking up properly is that when you do design, you can go here to design, and you can update PCB document, and they'll create an ECO. Right, and it's if you see here, we only have stuff generated for the main IC and the capacitor. So that's a good indicator that our resistors are giving us troubles. So one thing I can do now, just because it's not working, might as well just go ahead and just just get rid of it from our library, right? We can just delete that. And we can go over to the other one too, the projects schematic library. And just delete this. Right, and I can just find another resistor. At the end of the day, it's like a resistor, like it's relatively fine. You can choose a lower tolerance too, so it's relatively in the ballpark of 10K. Right, and it's like that's fine. You can, one thing I'd always do too for I2C is because you don't know if your design will work at 4.7K. You don't know if it'll work at 10K, right? It can even go at 20s. You can even go up to 50K, right? But it's more important to just, what you can do is use an oscilloscope to see how good your waveform is, an LCR meter to optimize it, right? Or what you can do too is just like, you don't have any of that equipment, you can just buy a bunch of different resistor values and just like pretty much test and trials it until you get the one that's actually working. So I'm just going to take this component because it's for a signal. You don't really have to worry too much about the wattage on it. You can press save. Right, I can open this guy up again. Go over here. I'm just going to refresh again so it comes back to the top. Right. Extract all. I'm going to run this. Oh, takes time to load. So I'm just going to go back here and see which one is the one. Yeah, this is the one. Then you know the drill. You just go to the PCB library, we copy what we want, the B, usually nice. Now we go here, we copy this. Now we go over to our own. And we paste this. All right, we save. We go here. And we paste this. And by the way, you can change the names too. Like if you think this is confusing, you can just change it. Right? Like this, you just say this is 060310K and call it a day. Especially in here when the footprint is like, it's CMP, right? 03412. You can make it more reader friendly, especially if you're sharing the project. And I'm going to save this. I'm going to have this. I'm going to delete the B's. Right. And now it's connecting to this one here. All right. Actually, let me remove this too. I'll just add it fresh again. There you go. Yeah, I'm talking after recovering from a cold is a struggle, but it's okay. We have to get through this, and it's a good learning thing to go through. And now we can see here. Beautiful. Now it's working. So when you ever start with an IC, right, or any type of design, usually what you want to do is set up a nice bounding box just to give a reader kind of like, what is this system? And you can see here I kind of failed tremendously. So here's this. It doesn't stay as a gigantic, yellow square, but you can just basically add transparency, remove the fill, then just put the border, right? Make it a color that you like. I usually just do like a nice chill color. And then what you can do too, right, is that you can also add text right here. And then you can do you can just up the text up a bunch. Right, and you just, maybe not that much. That's kind of going a little bit crazy. And then you can just say SHT41, right? And then you can maybe write sensor to tell them what it is. That's something like you can have something like, you can call it the MCU, and then you can have a separate window for the debugger. And that's a nice way to kind of give a visual representation of what this is. If it's a part of a big sheet with a bunch of other sheet, you might want to do another one of these over all of this and be like, this is the whole system that's in play here. Kind of like when you have like a basically system work breakdown, like a SWIBIS, then it helps make things more organized. But we're going to need a lot more room, so I'm going to move these over. And the next thing you want to do with ICs is that you want to add a net label. And net label is basically like, this is a connection. You wouldn't want to add it for power just because power has its own net labels. That's relatively nice. And you can kind of just do the symbol here. And then what I'll just do is like, we're going to power this sensor with 3.3 volts. We can do 3V3. That's a nice little indicator, as well as we're going to need ground. Ground has a bunch of them. You have chassis ground, which means it's connected to like a physical circuit. You have earth ground. You have a lot of different things you can use. Like you relatively just go use this one. You can use another symbol if you have multiple grounds in your design. Right. And then, like I said earlier, you want a net label, especially for signals. So if you don't put a net label, Altium, when you do the PCB design, will give you a random net. And then it's going to be confusing what you're routing, because sometimes you're like, is this an important signal or is it not an important signal, right? And you want to be really descriptive with your net label. So maybe you want to call this like this a SHT SDA, right? Or you might even want to say like, this is an I2C line from the SHT sensor, right? And then on another schematic over here, imagine you have another schematic down here. If you want to basically connect these 2 points, you can do the same thing as this, right? We can basically have this, and this is the same thing as it being a pull-up, right? And the reason why you don't want to do this is kind of just hovering here. It doesn't really make a lot of sense just to have it down here. So it's usually nice just to pretty much, if we delete that, we can just move it up here and keep it like part of the system, right? And this text will get in the way, so we could just hide that. Right, and then we can basically have that there. I'm going to shorten the name just because the spacing is going to be a little bit awkward because I didn't give ourselves that much space. Right. Then I have these two here, and what we can do here. So I'm going to move this guy down a little bit more just because I need more space for pretty much everything. And then now we can have this here too. Right, and then I can also move this guy up a little bit more. Right, and just make it look nice. Usually PCBs have like a top left to bottom right. So it's like the first item to the top left would be like U1, and then you have another IC down a little bit over here. It'll be like the next number. And then the next thing we want to do is basically copy this resistor over here. Right? And then these are pulled up just by 3.3 volts. So you start at the top left, go down to the top right. Right, and if imagine you can, as PCBs, you can actually, you have a lot of options, especially across different circuits. Like you have ports here. This is good if you have different sheets. So you can have multiple of these sheets over here, right? You can use it for different systems, right? And then you can use these ports, and that basically tells you, and you can have like a system level diagram that basically uses these ports, and that's kind of how you can tell if the PCB, like you want to use net labels for things that are internal to the actual schematic page here. Right, so if it doesn't leave this schematic page to another schematic page, then you just want to use nets. If it leaves, you want to use either a port, or you can use a harness connector too. This is good for like if you have SPI. What you have here, this is a port, and now you can have a harness entry, and this is for all the different wires. Right, and then you have a signal harness here. And then what you can do now is put the port here. Right, and the one thing nice about ports too is that you can tell if it's output, if it's an input, if it's bidirectional, and the verification or the system will tell you if you have two outputs together. So it means two things are driving it, which doesn't make any sense. Then what you can do is come over here, right, and then like the nice thing about nets is it makes you be flexible. So what you can say now is like, oh, this port is not connected to this wire. Right, you can also put down here, right? And imagine if we had like a connector page where we have like a schematic page where we have all the connectors, and then we'll basically just pull up a port with the same name here, and then we'll be able to pretty much use the same harness numbering to make sure we get all the right signals out. So it's another way to basically connect the board to a different schematic that's in the same project. So I'm just going to delete that because we just have this guy here. Right, and the next thing we need to do also is we have to take this. I'm just gonna hide that because it's relatively long. And we have this decoupling capacitor. And sometimes for schematics, if it's like this guy has to be relatively close to VDD, I'll put him right next to VDD or really close to it just to signify, like, if it doesn't make sense to have a capacitor floating out here or really, really far away, because it's just like, is this a decoupling capacitor or does this serve another purpose? Right? Well, let me undo that instead of just nuking it. And then now, like the last thing we said, we're making a physical board, so we want to make sure that we actually have like a way, not a USB connector. Oh, yeah. But we want to make sure that we have a way to connect to it. Right, and then we can go to connectors, and hopefully I find something that's not atrocious. And you have to think too, how many signals do we have? We have SCL, we have pretty much, I'm going to call this I2C SCL. Right, and then we have pretty much like, we need another way to connect to this. So one thing we can do too is that we can do, so if you want to be able to connect this into a breadboard, you want something with the pitch, right? We want number of pins, so we have one ground, we have VDD. Sometimes you can double up ground. It helps reduce like loop inductance or like ground loops, right? And then you have these two signals to keep it simple. We have 4 signals, so we'll just have, or not 4 signals, we have 2 signals, 1 power, 1 ground. 4 connections, and we can just relatively just pick number of contacts 4. You can always do more. You might find one that's cheaper, more simple, number of rows. I just want a simple one. And then pitch. So if we're going to be putting this into a breadboard, we want our pitch to be the same size. We don't want our holes to align to the breadboard holes, right? And then we have something. And usually if you're feeling really lazy, what you can do is just pick any connector here with like a diagram. It's actually very surprising that we don't have more connectors. Let me see. There should be more options. Something like this would be great, but it does not come up. Yeah, so we only have a small amount of numbers, so let's see what our options are. So maybe having the number 4 might not be good. The most important thing is I want a single row, just to put it on the edge of the board, as well as I want the pitch to be 1.27 millimeters, so it's able to fit into a breadboard. Right, and then we have the Milmax. These guys are pretty expensive, and then we have this one too. And then we have to make sure that we have, for the number of contacts, it's more than 4. So we can do 4, 5, 6. Ah. And it's still giving us all these bad options. I did this yesterday and it did not give me such bad options. Honestly, we could just pick something and go with it. But I kind of showed you how you're able to look at the different options, right? And how you're able to select them. You usually want male to male. Oh no, that's another awful option. Wow. Oh wow. Okay, so Altium is just not giving me a break today, I guess. But we can just keep it running and keep it going. Number of positions. We'll do 4 or 5, maybe. Okay, here, this is something that's a lot less abysmal. I believe it's 2.54. Is it? Here, let's look it up just to make sure. Pitch for breadboard. Oh my gosh, it's Donald Trump. Oh, it's actually 2.54. So I was wrong earlier. So it's always good to just double check things so you're not making any mistakes. It doesn't hurt to double check things, right? At the end of the day, after we do this diagram, you want to have like kind of a design review to kind of make sure you're running everything correctly. But now we have a connector that actually works. And then it's also SMD2, so we won't have holes. Right, and then we'll have to use VS to go to the other side. And then I'll just save that. You know the drill. You basically just take this guy. Right, find the one that I just downloaded. Extract all. Run this. I'm going to drink water. Hopefully it's not the most loud thing in the world. We can extract. And now you have the components. And what we can do now is go to PCB library. Copy. You can go to the schematic library for this guy. Copy. Go to our PCB library. Paste. Also, save. Start is gone. We're all good. And now you go over here too, and you paste. We can fix this name here and just put it like to the side here. All right, and we keep that there. That's fine. Right. Now, you make sure we can remove this too. Just maybe that's the reason why the resistor before was giving me such a horrible time. Now we can just browse. Pick the one that we have. Okay. And then now what we do is we go to this guy, manufacturer part search, and we just add it to the link. Boom. And you see right there, the description changed. Now we can basically click on this now, add a supplier link. It'll choose the comment. Hopefully it'll choose the comment, and the comment comes up, and that just makes it easier. So the person in the future who's looking at your design knows what item you actually picked in the store and what specific like code you picked. Now we can place that. So now, you know how we were talking about nets, right? Oh, by the way, you can press X to kind of flip it around and Y to flip it around, just so, and then space to twirl these things, and then just a heads up too, just in case it wasn't noted earlier and you don't remember from the tutorial. You can press Control W to click wires. I am assuming that you picked up some stuff from the tutorial, but it's okay. If you have any questions about anything, just reach out to me and I'll be able to help. Right, so now you can make it really messy by like connecting everything to here. And the one thing I love about connectors, also you can just make another bounding box and call it connector 2, because this is a small system, but in the end of the day, it's all fine. What you can do now is just basically copy things over, right? We can have ground connected to 2 pins, then we can have signal, right? You have I2C here too. Ooh. And now we have those 2 there. Now we have a connector. And now what you can do too is that you can pretty much type numbers into the designators. This is the second resistor, and we're going to go incrementally. Right, so Altium also has a way, if you're really trying to do something fast and you have a really big circuit, you can just do these last. There's a way to auto-generate it, right? You can do auto-annotate schematic, and you can have it automatically generated. Sometimes it can be a little bit funky, but if you don't care, and you're just trying to be fast, just go for it. Now what we can do is, we've done our schematic, so we want to validate the schematic. And then sometimes because I'm the one that pretty much set up all these libraries, I won't have any like spice models or anything in here for simulation. If you copy it directly from, basically you can click and drag from the manufacturer part search, right? I believe if it doesn't fight me, oh, it is fighting me. But pretty much, like a lot of times you can use like the workplace, or you can click and drag to replace things here with the manufacturer part search. But the problem with that is that you don't have control of the actual component and the paths that you're putting down, because when you imagine you make a mistake and your boss is like, why did you do that? You can't blame it on the path that you download online. At the end of the day, you're the one that put it there. So it's always good to like just look through everything, right? And just make sure that it's all the right size. right? Like here, we want something close to 1.6. That's close enough. Here, we also want something close to 1.62, right? That's close enough too. And then here, right? I'm just gonna trust that one. But here, right, we have the pad too. We have the diagram, and basically, you want to basically look on the data sheet where the package is. All right, and where we have the pad layout, if I ever find it. And here, they have a suggestion. So they have a 0.5, right? What we can do now too, exit out of this, go here, properties, right? We can do pad vertices and edges, and that'll make it so we're actually able to snap onto the pad sides. And this is 5 millimeters. That is good. Center to center, 1.4. It's 1.4. Height of the pad, 0.3. That's 0.3. From pad to pad, side to side, 0.8 is 0.8. This is basically square on with what the manufacturer recommends. Whoever does this in Snappy EDA is not trolling us. I've had one with the new BTA40 where all the pins are slightly shifted up from all the conversions that it went through, from mils to millimeters back to mils and so on. That's all I can think of. Or if you actually using your design, it would just wouldn't be correct. So it's always good to double check these things and make sure, because a lot of times it's like maybe 2 out of the 10 of the components, right, on Snap EDA, or even the libraries you get from Altium might have something incorrect. So you just want to do your due diligence. So now we want to validate. If nothing comes up, you're probably in a good place, right? Sometimes you might get things where it's like power pins does not feed into input, and that's more for the simulation. So you can kind of ignore those type of problems. But if you have like a component or like a library, right, and something's like disconnected, and you do this, it'll tell you sometimes that there's a floating wire, right? And it's good to fix that. So repass the validation check, right? And then we'll also have design rule check that we'll do that because we upload those design rules, right? But the next thing we want to do now is update the PCB schematic. Do validate, execute changes, and now everything pops up here. So one thing I always do when you have a PCB start out is that we're making a 50 by 50 board. I'm just going to put down mechanical layer 1. All these mechanical layers are pretty abstract and what they're used for. You can see that online that people kind of have like this standard of what they use for each one. Like 1 is outlines for the board. 15 is like component outlines. So you see here, this would be like a 15 outline here. And then like the hash lines here, it's just pretty much the 3D model. So if you just move the 3D model off of that, right, then the hash lines will go away from the actual pad. Red is the copper layer. It'll be blue if it's on the other side, or maybe like you're not going to put components in the middle layers because that's physically not possible, but you can try. Right, and then right now you can see I'm having a hard time clicking on this thing because I have a setting to make these things really, really small. And I can just make that 1 millimeter, right? And then we can move over to basically mechanical layer 1, and that makes it easier to grab. And you can also press Q2 to go into millimeters. So what we can do now is that we can just do 50 by 50. Right, I just put it usually around here. Altium has a weird bounding box, so it's good to just kind of like put your design where the original black square is, and then you can pretty much set it here. You can put this somewhere in the middle. Now move this to 0 by 0, right? At 50 by 50. So this is basically the whole area that we get for the board. So what you can do now, let's start putting components down. What I usually do is that sometimes I'll like leave this larger, and just like if you have a bunch of different little systems, you can basically like do the whole design over here on the side, or all the routing here on the side. For example, if you have like power electronics, and then for like if you have a big board area, what you can do is then do the routing Control W, right? And you can basically just connect everything here, and then not this terribly, of course, but you can kind of like connect it there. And then once this is ready, you can highlight everything and then move it over to your main design area, and then you can use that to connect to other things on the board, right? So you can have it's a nice way to organize your work, and then you can just group them up first to the systems that they have, and then you can kind of work on everything little bit by bit, because it's kind of hard if you don't break down the problem and the issues, right? And the nice thing too about Altium, imagine more if you're deleting all these traces for fun, but what you can do is that you have right click, find similar object, and then you can do pretty much same. I'll do any, because if you do any curves, it'll come up as like a curve instead of a track. Okay, and then I can just say the same width, not different, same. Apply, and now it highlights it for everything. And now what I can do is pretty much just like take all this and just, delete it. Oh, shoot. Let me see this, find similar objects. Same. Now I can just press, it keeps going here. Right, but you can just go over here, and then you can just cut that. And then hopefully I don't paste it back in the monstrosity that I was. But one thing too is that you can press space to kind of like spin the component around. Another thing too is when you're doing any type of traces, you can hold shift space, and that'll basically give you different bends and curves and all that. And control W is just like a way to pull up a trace. There's different routing options here. There's a different differential pair tuning, so good to play around and look around. Right, and then similar to the data sheet, right, we have our I to C. We have our decoupling capacitor. So our decoupling capacitor, we want relatively close to minimize loop inductance. We want to make the pin here be right up against the component, right? And we want the silk screen not to be inside of it. Another recommendation too is when you do any type of PCB layup, you put 1 millimeter for the placements, just so then, like, for example, imagine, right, you have like 25 millimeters and you do this, right? Or you do something like this. It's like, you can do this, but it's like, if you actually look at this, right, that's 0.5 millimeters of space. That's a lot of soldering irons will struggle to get in between that place, and you'll just be shorting these by accident if they're not meant to be connected. So by sticking to 1 millimeter, right, you're able to have a kind of a good standard where you keep these things away from each other, right? So then it makes soldering easier, because now you have all the free space around here, right? And then what you can do is you can go down to the lower grids, because if you notice, if you're on a higher snap, your traces will snap to the grid if you have the grid on, which I always recommend having on. And then if you go to the lower ones, your traces will be able to have more freedom, because you can kind of place them anywhere. So you can pick and choose what you need, right? What I would usually use, not the Cartesian grid editor, but yeah, you could edit your grid. And I brought that up by Control G. And sometimes it's good. Also, one thing that's good too is that you can change your snap distance or your axis snap range, and you can lower these if you ever want to not have it snap either to like one of the grids here, or snap automatically to one of the components, right? And right now I have the vertices and edges off. But now if you ever imagine if I really want to just click right here in this space, it's just impossible, because it's always on the corner of this pad, right? So it's good to go into your properties and just untick things or tick things depending on what you want. Same thing with the board shape. Like, imagine I really wanted to, snap here, but because my grid is not working. So what you can do is you can just go board shape, and now it's just snapping here. So you have a lot of options. It's good to play around and know what you do. Now that we have everything on the board, what I usually like to do is just like make this relatively small. You can do 0.01, it'll approximate to pretty much nothing. And then you can go to design, you can go to board shape, and you can divide board shape from selected objects. And that kind of just like gives us a bounding box of where a PCB will be. Go back to 1 millimeter, and now we can just kind of set everything up. Right, it's like, imagine, think about it, you want to always route your important signals first too. So it's like, I probably, right, want to have this maybe here, And then I'll have this guy here, similar to the design, right? I'll just put this centered, and then I'll maybe just call it 9mm here. This is good. -10 is nice and clean, right? It's good to imagine if you're a mechanical engineer, you had to design a PCB for this, and then you told someone like, hey, this is from the center of the PCB, or from the edge, it's 0.0001 millimeters away, right? It's good to kind of put it in a nice places just to make it easier on anybody who's doing mechanical design. They can tell like, oh, okay, this is relatively like, 5mm from the edge or whatnot. And then now what you can do, right, is that you see here, we have that guy. We have to also consider too, compared to the dip, where we have to consider these cutouts too. So then the heat from all the random components, imagine we had another power, like a heater element on the PCB too, that would basically seep in and power. And we want to do something that's called thermal relief to kind of fix that. So what we can do now too is that you always want to focus priority signals on this board. The priority signals would be, SDA and SCL. And what you can do too is that a lot of people online and RF professors and any type of like professors that kind of specialize in noise will tell you to pretty much just go with like 8mm or 8mm or a 6mm trace, right? A JLC 4 layer, I believe you can go to 4, but remember I told you if you go too thin, they might make more mistakes, right? And what you usually want to do for traces is kind of just want to maximize like as straight as you can, because that's like no impedance changes along the trace. Here there'll be a small like infinitesimally high like trace compared to like if you have a trace that bends really sharp, you'll have this bend here will have like a higher impedance. So it's good to kind of minimize the amount of bending you do, right? And go for a lot of straight shots. Right. And then we also have to put the pull-up resistors, right? And what we can do too is that we can basically snap the tracks, right? And we can just bam. Make sure this is like a decent number too. We can even this out. Actually, never mind. I snapped right on the track, so that can be there, but we can make it -3. So at least that's even. Right. Along the y-axis. And then what we can do now is also click on the pad here, snap that down. And I'll also keep this -3 so it's like the same length. And now the next signals, power is like the energy, right? Travels very closely to the actual trace. So what you can do is just kind of, you can get really flexible power. You can route power like really around, right? And what you can do too is make the trace a little bit more bulkier too, right? So here I have a more bulkier trace, right? And you can line that up over here. But one thing I want also to go over potentially, right? Then we also want this guy here, right? But you don't want it to be too tall, because imagine if you also have a spectrometer sensor too, and you had a light coming from the side here, right? The capacitor might block it, so you want to basically account for that. For this guy, it doesn't really matter, right? To basically maximize or just have the best ability, you want to minimize your loop inductance. So you want the 3.3 really close to the 3.3 on the chip, right? So what we can do is just like make it easier for us. We can put it on the other side here, tilt it over, and then we can just basically add a via, which is like a portal from one side of the PCB to the other. Because if you look here, if you press 3, right, 1 is also the board editor. I always recommend using mechanical layer 1 as the board editor, because in a lot of programs, a CAM operator, which is the person who will look at the PCB when it's at the manufacturer, will usually use mechanical layer 1 as a reference of what your board outline is, right? And you'll see too, when we make the cutouts, that I use mechanical layer 1 to draw it. And then by doing that, you keep the board outline there too. So it makes it a lot easier at the end of the day, compared to if you use this to make a custom board, then you might have to trace the mechanical layer 1 around it, right? So that's something you have to consider too. Right, and now we have here, right? I can basically go up to here, say 8 mil, right? And now I can do hold Control Shift, and you get like a via down, right? And then this can just pretty much, no. Pretty much, yeah, I want to go to 4, but I kind of made a mistake by putting it down on 3, but basically now we have these connected to each other, right? And you can move this closer, and I would recommend going down on a smaller grid, get like a better, like this is pretty much like a straight shot to the component, but you have to also consider to the via here. If you make it too close, you have the solder mask here that you have to make sure it doesn't get too thin, or this is just going to be a straight trace. And then when you're trying to put solder in here, it's going to get in the hole here. It's going to try to move over here. You get a really uneven job. So what you can do too is you can go to the via as well. And then like one thing I always like to do too is that this is relatively like a safe size, but I like to go maybe a little bit larger on my vias. Right. And that's fine, I believe. And you can run like a design rule. You might get a lot of design tools and you go design rule check. And you might get a lot of errors at first. But right now we have mostly the unrouted errors, which is something that we'll fix when we route the board. Right? You have ground you don't really have to worry about as much, right? Also, for some boards too, imagine if we like basically lined this or had this basically go on the blue side, right? Because you have to think about when the signal travels down through the board, there's no ground directly under the signal, so it won't have a return path, because for all signals, their return path is directly under them, pretty much. And if you don't have a return path under them, you'll have increasing fringe fields cause noise to other circuits, right? And it might cause instability in the system. So one thing you can do is that you can always put a via. So imagine if I was using this to go down, right, to another layer, and this went off to another board. What you can also do is copy that and put another via down, right, and make it ground. So now it's relative to now that the via here, right, it's the same thing as if we had a ground port right underneath here on the blue layer, or like right here on mid layer 1, right underneath the red here. The red will be able to reference the ground layer on mid layer 1. But same thing, how if this is going through the board from the top layer to bottom layer, it'll now be able to reference this ground via, right? And then it will reduce the amount of fringe fields, like basically emit off this line going through the board. So if you have the space to do it, I always recommend putting a ground via next to any type of signal via. For power, it doesn't really matter, right? We don't really, if we can, it's good to put our put our priority signals, which is basically I2C in this case, on the top layer. You also see too, when you do impedance matching, that the top layer allows you to have smaller traces. If you do it on the back side, the traces will become too large for you to actually like connect. Because imagine if you had to like connect the trace here, right? But the trace is like 40 millimeters because that's what the math forces it to be. And then, that might be say 3 millimeters. And you see, like, imagine trying to connect this. It doesn't want to connect anywhere. Even, it's just too big to actually connect to anything properly, right? It's like a big earthworm. And that's something you have to be careful of. It's not that drastic, but it's pretty much close. And another thing too that's good to know about is polygon pores. So imagine you had a bunch of different, like if you do power electronics, you usually want nice like polygons. And what that does is like you have this nice plane of copper, and that helps increase the capacitance and stability of the network. And then you're able to connect all these things together, right? Similar to this, right? And then this. And then what you can do now is that you have a polygon pore, and we can make it 3.3 volts. And what that does now, this could really be a 2-layer board too. This one, I just went through the steps of doing a 4-layer board just to give you an idea how to do it. Just because the PCBs that we were making might be a little bit more complex than a 2-layer. So it's good to give you all your chances, because if you're able to make a higher layer board, right, like a 4-layer board, it's easier to do a 6-layer board if you know a good stack up. And then you're able to do 2-layer too, right? But now you see all these guys are connected to each other. Right through the 3.3. You can also go through here and reset error markers, because right now it's telling you that these aren't connected, but they are. We can run another design. But you can see here, right, we have these now connected through a polygon. And one thing that you can do too is that you can go to mechanical layer 1. You can actually draw a polygon. So you have the line tool, you have the circle tool, right? Imagine if you just want to put a really nice like circular polygon layer, and then you have the tools and then convert, right? And you have all these different options. Now we can basically create polygon from selected primitives. And then now we have an outline. What you can do now is change the top layer. So it's now, then we can do 3.3, right? And now you have a lot of options you can play around with, right? Like here we have this polygon here. Oh, 4, right? Well, I'm having a hard time selecting it because of the outline of the polygon. I didn't do fill, and then it's now like a 1.1 millimeter. Okay, so let me undo that, and let's choose something. Like if you see here, solid now. Now if you re-pour, see now it's a red circle. Before I had this as a 0.0001 millimeter line that doesn't exist, and then when you first have it, it's just the outline of it. So that's why it was fighting. But now you're able to have this polygon pour here, right? We can go back to layer 1 so we can move it around. And that's a way that you're able to get unique geometry, right? In your design, right? So now imagine if we wanted to make that a circle and we just want to put the circle here, we can do that, right? And then one thing too about polygons is that sometimes they won't go over each other. So one thing I always do is go over here and you can do pour over all same net objects, right? And that'll make it so then it just goes over everything, because sometimes it won't pour over a different object of the same net. And that basically makes it so it's able to do that, right? I usually always turn that on. Another thing too is you see here, this is a thermal relief. So it's really similar to how we have kind of like the cutout for the SHT41's dev board. What thermal release does is it basically makes it harder for heat. If you put it, like imagine you use a soldering iron to heat up this pad, the heat will have a harder time transferring from here, right, to this larger copper plane here, which makes soldering easier. But the downsides of that is that you have these little tiny, infinitesimally like small like bridges here that are very easy to tear. So if you're not really comfortable with soldering, what happens is that you might accidentally rip off the pad, and that's a problem that might happen, right? As well as one thing you can do too is that you can just turn that off. For higher power boards, a lot of times for power electronics, they'll just get rid of that. One thing too about resistors is like when you put down these components and use hot air, the type of like flux or the paste that they use, not the flux, but basically the soldering paste that they use, will pretty much like cause the heat and how it like melts, right? If you have a temperature difference between the two pads, it can create like a torque on the SMD component, right? And it's called tombstoning. And then what happens is that the capacitor will actually like kind of tilt upwards and point towards the sky. And the way they counteract that is that you make sure that the amount of copper coming into it is the same as the copper going out of it, right? So imagine if we had like a really massive trace going right into here, this would have a hard time heating up, because it's like you have so much copper dissipating the heat. The heat will be here all pretty much like, stuck here. So this will melt first, and then this side will basically be the one touching the PCB, and then the I2C side here will be the one tilting up. So you want to kind of keep it even, right? And then one thing that I usually do, this is a small PCB, and if you have a good soldering iron with good like energy, output, you can basically go to Polygon Parser, go to Polygon Manager, right? And what you can do is do new connect style. And you can pretty much just change everything to direct connect, right? You can do specifically, so this is the through hole, this is for SMD, this is for VIA, right? VIA makes sense just to be direct connect, right? And that way we report this, now the thermal relief is gone, right? And you can also, like, for polygon actions, you can edit polygons, you can resize polygons, you can really play around with it. So you have a lot of things you can do. All right, so you know now that you're able to draw and basically use the conversion tool to basically make polygons, right? As well as we can do the same method that we used to make that polygon circle to make the cutout for this guy. Right, so one thing we want to do now, right, and also one thing to imagine if you're trying to like put a trace down from here, right, over here, it's going to complain. So one thing I always do too is that when you have a polygon, go to the polygon, you can either come here and you can do polygon actions, and then you can shelve all, right? You can do it from the polygon management window, and then you can basically bring it back later. And what this does now, imagine if you want to design, and when you bring it back later, it'll try to like basically go around this trace and not like fight it. So it makes it easier for you too, because when you have like rules or conflicting, sometimes it won't let you lay a trace through it. So it's easier just to lay the traces down when the polygons aren't there and add the polygons later. So it's good that you're able to hide them. So now, like I said earlier, we're able to pretty much take our line tool and go to mechanical layer 1, which is the board layer, right? And we can just kind of like make a nice geometry here. And I can go back to layer 1 here. Maybe not that small, but we can go here, right? And we can kind of just draw a nice little, area around here. And I can just get rid of that. We can copy this here. Right, and we can just have that there. And then I can kind of just center this whole thing here. Right. We have the center right here. And then now this is like, right, we have that there. Oops, I forgot everything else. Doesn't matter if it's centered. You can do like math to find out where it needs to be. Right, but at the end of the day, what I'm primarily doing is just like, just trying to show you how these tools are used, different things you can do, right? So now we can like, we can come out here. This might get a little funky, but we can just pretty much like make a nice little thing like this, right? And then now we can pretty much connect that there. Because you see here that this radius is kind of a little bit weird, so we can bring it in, right? We're gonna leave that little tiny weird nub there, kind of there. And then we can also like basically go off if you actually have vertices. Right, and we go back to the red layer and we can kind of see like, it's hard sometimes to like snap to things, right? And get distances. But we can do Control M to kind of snap to where this is. You can see where the X is. This is, well, I missed that completely. But basically we can kind of see where that is, and that's going to be 3.45. Oh, 3.45. Okay, I'm just going to take it. We're in business now. So now one thing that's nice too is that imagine we're trying to highlight this. You're selecting everything there. What you can do is go back to mechanical layer 1, do Shift S, and now you're able to cycle and the different layers. So now all the other parts that aren't part of this mechanical layer 1 is hidden. You still see the board outline. That's the one reason why I like using mechanical layer 1, right? Or 15 to draw polygons and geometry. Another thing too is that if you, this isn't really that useful, but you can also, by the way, this is from Control F if you ever want to look at the back. But one thing, if you hold Shift, you look around, your controls might be a little bit different than mine, but you can also do Shift S here, and it just hides the mask, and then just see the copper, and then you can just see how your copper is. It's a nice little visualization. But basically now I can press Shift S, select this guy, make it like infinitesimally small, and then I can use this and then conversion, and then you won't be able to bring up a board cutout unless you have a board cutout present on your circuit. So this is one way that you're able to create board cutout from selected primitives. And now you have that. Right. Now what we can do now is that we have that. We can now take the geometry that we have here and kind of like narrow it down, right? And we can kind of make it even. We can basically find out how much space we want this PCB to actually take up, right? And I'm really happy with that. So what we can do now is like, maybe I want this to be a little bit more even. Not 12. That's definitely not going to work out for us. But what you see now it's even. And what you can do now is you can go back to this tool over here, mechanical layer 1, and you can click here, and then you can basically shift space. You want 45, if you want some bends, shift space lets you basically cycle through these different options. And then you can just do the 9090 tool, and then I just kind of click all the corners, add corners to our PCB. A lot of times it's good to just do math, and then you want to make sure that this isn't actually made a mistakey and didn't connect these. Oh, didn't do it again. There you go. And now you can do is just select the whole corner here of the original PCB, delete that. Right. And what you can do now, if you want like nice corners, right, you can just now move that. You can see how the radius changes. Right. So we have this is 1.1707. And then now I can basically, just play around with this. Have the time of my life of how this is. Right, and then we can just match the radiuses. Oh. It's like this is still a little bit too sharp. Now it's nice. It's even. We can click this. Right, and then we can basically unselect this. I'm pretty sure. Oh, never mind. It's fighting me. Okay, well, I'll just go around it. And then what you can do now is you can go here, board shape, find board shape from selected objects, and now you have the board shape. So one thing that's nice too is with polygons, you can go over to the tools, polygon pores, right? And now you're able to go to polygon manager. You can do new polygon from board outline. Imagine we just want to have 3.3 on the whole board, right? What is that? Is that I think that might be something I created before. It's 0 square feet. I'll just delete this, because that might have been something I made a while back. But we can just pretty much, that's that guy down there, but we can do polygon from board outline, right? Then we can do no net 3.3. And then we can do report, force report all, yes. And then we can do new polygon from board outline. And then we can basically call this ground, right? And then we can just apply, and then always like do import overall same net objects, apply, right? Okay. And this one would be on the ground layer. Oh wait. So that guy is the ground, so I want that to be on the bottom layer. This thing is on the top layer, so I want this to be here. This is kind of just doing nothing. I kept accidentally making incorrect ones. Just to be clear, what's happening is that I'm just creating pretty much these polygon shapes that are based off the outline of the board. right? And then we can do 2 is you can unshove all polygons, so we can get back to when we have reinforce all polygons, apply, right? Yeah. And you see now, hold on 1 second, let's see, let's report this guy. Okay. See, this thing is a little bit confused now because you have this polygon here, and what you can do too is you can send polygons from front to back, and it'll prioritize like which one you want. Right, so if you have something that's really important, you want this geometry to take over another one, you'll basically put it towards the front of the priority or the queue, and how it's like basically drawn up. Because like I have this large polygon part, I might just delete that one. Right, but now you see, like, I didn't want to put a copper plane all the way out here, right? And I also don't want to have thermal reliefs again, because it's just the way that I like to design my PCBs. You can have them if you like them. It doesn't really, the actual resistance to the pad, right, isn't really that different compared to if you just had direct copper connected to the pad, because these little lines here are infinitesimally really small, right? So they're pretty much non-existent. It's just mostly there for thermal resistivity, right? And just basically stopping heat from escaping from the pad. But that's also, it could be a negative too. If you have any power electronics components, they use the PCB's copper as a way to dissipate heat, right? So if you have this pad, it'll just make it so the component isn't able to dissipate its heat into the copper. It'll just overheat itself. So you want to consider things like that. So one way you can do that, from stop it from basically having the copper come up to here, so I can go to a larger grid again, and I can do polygon port cutout. And you can basically press shift space until you get the nice rectangular bit. You made this here, top layer. We can copy that here, paste another one down around top of it. You can see here, right? And then now I can switch this as the bottom layer. And what we can do now is that we can press right click, and then we can do polygon report all, right? And now they're not there, right? And we can basically, if you want to extend this down, you can extend this down, right? We can do whatever way you want, right? And then at the end of the day, right, you want to just do your due diligence to make sure, like, if you had a really hot PCB and you found out this copper plane being too close to the next revision, right, you just make it further away, right? A lot of this stuff sometimes will take multiple boards, multiple attempts, right? And you're learning over time, and you're getting good intuition too while doing it. You can do like a lot of thermal simulations on ANSYS and a lot of other things like that, but it depends if you have the time to do it as well. A lot of places will have pretty much like a dedicated person, right, for ANSYS, right? You have a dedicated mechanical engineer for ANSYS, and then they'll be able to do that too. Also, one thing too is that when you have vias, because this is going to be used in a greenhouse or a temperature humidity board too, you have to consider that, like, this, right, it's going to get wet, maybe, or humid. The surface might collect water, and there's ways, like, there's thermal compounding you can put over it. Not thermal, but like some type of conformal coating that you can put over it, right? But one thing you can do is just go manual and then just tint the via, right? And you can do also that trick that I told you earlier too, to find similar objects, and you can just find vias of the same size and apply, and then you basically can just change it for all of them, right? So it's easy to edit a lot of objects at once with that control F, like a control, I mean, not the control, but you define similar objects, right? And I flip the board. Now, what it wants us to do is to route power. And power, I have it on top of here. See, right now I'm having a struggle. If you see here, I move it over. So this is why I always say it's good to do your traces first and then put the polygon on. But I just needed more space for the 3.3 to come in, right? And then you can kind of like see over here, you can kind of adjust this, make it a little bit nicer, right? This is the demo board, but you can, what you want to do too is like for vias, you want to give them space. So it's like when you have a lot of pins close to each other, you kind of want to bridge it off and get space away from them. So then they don't like basically couple to each other and have noise, right? And then now you can just have a ground plane now. Let me go bottom plane here. And now we route ground. Right? And now we're in business. We can also connect that directly to the via. Right? We can move that over. And now after all that, we are now completed. Right, we have our connector. We have all this going on for us. It is the most off-center thing I've ever done in my life. That should have ideally, we should have, taken these things away real quickly. And let's see if we can make a quick edits. That's the one thing that's going to be annoying about JLC, not JLC, but PCB design, right? Is that you might accidentally have something like this, and you want to kind of move it up. And then it's like, you see, I kind of just rip off all the traces, right? And then you're like, oh no, which side is like the middle too, right? It's like, oh, this is not good. Right, this is not good at all. And you can do bottom overlay, which is basically the silk screen or the paint that you see, that the white one, right? And then you can just put that over here. It's okay if it hangs off the edge a little bit, because it's like, it's going to give you an error, but what they're going to do is just cut out this part of the board anyways, and you're just going to be missing whatever was past the edge, right? Now what we can do now is just delete these little tips that come off there and just kind of just finish the trace there. And like, I didn't do any math, I just kind of ballparked it kind of ish in the middle, right? If I really wanted to be careful, there's things called guidelines, right? And what those are is basically like, if you have properties, right? I believe it's somewhere here. You can have grid manager, and you can pretty much add grids. Not grid manager. What is it? I think it is a guide manager here. And you can add like a horizontal guide, right? And you can put it at like 0 degrees. Now you see you have a line here. So you can also snap to it too if you have the right settings on, right? And then you can basically use that kind of to set up your measurements across the circuit before you start doing any type of like work and layout work, so you know exactly where you want to put stuff. So maybe I want to do like a grid line for the center of the board, a grid line of where the center of this is. I've done that before for a lot of optical sensors. It helps out a lot. And what now you can do is place this guy back after moving it. Right, place this guy back. And then you go here, polygons. I usually like going into the polygon manager. Sometimes when you do shelve all, like unshelving from there, it kind of like resets it. But I can unshelve all polygons, select them all. I like turning off the thermal reliefs. You have to make a really big PCB with lots of copper for you to really have a problem with the ground plane, or a really weak soldering iron. But you can find a lot of good ones like the Pine Sol, right? That's like the F and Iris one. That's like the H2, I think something. And that's also 100 watts of USB fast, like USB PD, like 100 watts on that. That's pretty good. So now we're done, and all we have left now, right, it's just running in design rules again. So you go tools, design rule check, run design rule. And I can see, oh, net antenna, what happened, right? And we have some unrouted connections, right? And you're like, oh, what is going on? Right? Why is it doing this? Oh, and it's like, oh, net antenna. It's just this. And I also don't have this connected either. And it's like, oh, I didn't catch that until now. Right now, I can basically polygon actions, report all. Right. What you can do too now is that you know where the paths are. You can pretty much just put the VS. We can just copy them from here because they have the nice ones that are already tinted, same size that we usually do. And then we can just choose ground. And it's going to give us a warning because we just pretty much like, slapped it right there. You can move it a little bit away to give it space. Right. You can really like center if you want to. Right. Sometimes you don't want to let perfection be the enemy of just good enough. And then you can do pretty much report all. And then we can just run traces here. And it's going to find us again, but we can just right click and then report all if you don't want to shelve the polygons again. And now, see, we caught a mistake that I had. We run design rule checks, we do it again, and it's 0. And then, for example, sometimes you have errors that doesn't really matter, right? So if you ever have any errors in your design, you can always just walk them through with me. For example, for the silk screen, it's just like the paint that tells you what each thing is on the PCB, right? If you have it here and you do design rule check, you're going to get a violation because it hangs off on the board here and it's board clearance. And one thing you can do too is when you close this, if you have a list of them, you can basically click on here and it'll jump to the problem. And then if you hold basically like control space and that, or a shift, or I believe whatnot, you're able to basically use your arrow keys, just go through these, press enter, then go down to the next one, press enter, and you can jump across the different arrows. I can show you how it's done. Once in a while, if you have a lot of errors on your board, if you ever make one that has a lot of errors, right? But we can kind of put that back too. And imagine this because the silk screen is really big. One thing too that we can do is that we can find similar, and then we can do, because we have it on either side, so it could be text, top layer, any, so that's fine. And then we want to have the same text and the same width, which is like the default ones I have. Right, and then we have that all highlighted. Now you're like, oh, what can I do for the silk screen? So now we go to the legend here, and we're like, okay, so it says here, oh no, not the AI person, but the width is 0.15 millimeters with a height of 1 millimeters. Okay, we do one height 1 millimeters, and then we can do 0.15 millimeters, and now we have smaller silk screen. And then that makes it easier to fit things if you don't have a lot going. Like if you want to, I mean, if you do have a lot going on, you don't want to spend all your real estate, right, on silk screens. But now you see how much I can move this over now closer to it, right? Before it was like it was already touching, so it's way smaller already, right? And then you're just now able to make it more snug, right? In old manufacturing, you used to have problems if you put like any type of paint over traces. This is on the top layer though, so it looks like it's over the blue one, but it really isn't, right? And one thing too, like I said, if we were done, but one thing you can do too is that you have the other layers. So I designed it right now if we were having like a 2-layer board, right? But we actually have more layers, right? So one thing I can do too is just change the bottom layer to also voltage. But one thing you can do too is just go over here to polygon managers now too, and I just want to like include the extra copper. It's good too. A lot of times too, if you put too much copper on one side and on the other side, what happens is that it can kind of like cause the board to warp or bend like a Dorito when it goes up through heating and cooling. So it's good to make sure you have a nice even amount of copper around the PCB just to stop any mechanical stresses like that from happening. And a good way to do that is if you designate a whole entire plane, right, to ground. And that makes your signal clarity a lot better too. Right, now that's going to be ground. Now we do a new polygon from board outline. Right, this will be the next layer. And that will also be ground. Right, and now we can just kind of look at here. one thing we have to do now is also copy this, paste it down again, change the layer of the new one to that one, paste it down again. Right, oops. Okay, so we copy it, paste it down again. Oh, no, I copied too many. Okay, you have to be good at this. Let me just make sure we don't have too many. Okay. Okay, now we're back to here. I just basically undid a lot of these. So basically I go to the red layer, right? And I'll copy this. And then I'll copy that. And that reference, put it down again. Then this will be changing the old one to that. Then I basically want to go to the mid layer, and then I can just click on here. And then I'll click the mid layer when we can copy that. Paste the new one down again, and then we can go to the mid layer, change to the mid layer 2. And then now we'll have it across all of them. Right, and now we have all the layers. And what you can do too sometimes is that you're able to this thing called via stitching. And that's something you can do. Like if you put down a ground via next to all your signal vias, that'll basically like you won't really need it that much, right? But what you can do too is just use a tool to stitch the two grounds together. It doesn't hurt. It mostly helps if you are able to put like vias or ground vias in the proximity, right? But you can add stitching to net. And then we can just say, we can just choose something random. This might be a little bit overboard, but right, you can also do where's complete tenting on top and bottom. Oh. Grid step should not be less than via size. Right. And then we can just change this to 5. Like, not 5. We can do like 1 millimeter, so it's like really sparse, maybe. Oh. Okay, I'll just put 3 then. Oh, okay. And the reason why it doesn't do that is because our top layer here is ground. So what we can do, because the machine won't do it, let us do it because we have this here, is that you can either hide the 3x3, right? But you can also just like, you know, you can also snippet polygons, shelf selected, right? And then all of these should now be green, not green, but ground. And then now we can do the tools, and hopefully it doesn't fight us. And this is the same way too that you're able to also do like shielding via shieldings for like if you have a lot of DC lines next to an analog line, you might want to do shielding or via shielding right along the analog line. But you have to make sure you do correctly because it could make things worse. Stitching to net, right? And now we'll just choose the ground, right? And now you can see it throws them around. And what we can do now is we can go to polygon options and we can just, oh, no, that's not there. And then we don't want to restore because restoring basically like resets what your connect styles are, right? But we also have to update the connect styles too because we add the new ones and it doesn't make sense for an internal layer to have thermal relief, right? Because you usually want the thermals, the copper there to be used for heat management, right? Or to improve like your current capacity, right? So it's usually good to do that. And then usually here I always like doing pour overall same net objects, right? And then you can do that. And then I can do polygon options, report all. Now we're back in business. This is now complete, right? And one thing I also want to consider too is like for theory, right? Imagine you had like a little tiny copper plane here, right? And then we have like, imagine we had a little copper plane here, rectangle. Like you notice you did a polygon fill and then you had like a random piece of pretty much, no, let me do a polygon pour. Imagine you had a random piece of like polygon here just hanging out. And we'll just make that 3.3. right? And this is basically called, I don't think it will actually do anything because it's not connected to anything, but it might be too small. There's a lot of reasons why some things don't show up, right? But basically we can re-pour. So yeah, this is fighting me, but imagine, just imagine. Oh, it's because this is the cutout here. So that's why. So imagine you have this here, right? Like this is an actual polygon pour, similar to what you have down here, and this is just like floating copper. So one thing you have to always do is make sure you always put polygon cutouts along areas like this to get rid of these islands, right? And you can see here there's an option to remove dead copper, right? And that's basically called the ground island. And what that happens is it becomes a resonant cavity, and all the fringe fields or noise from these lines will basically jump to this cavity, and then they'll bounce around and get higher and higher energy, and then it'll lead to worse noise if there was no ground there. So that's why sometimes, right? And then like to fix that, you might put vias down, right, on each side, not vias this big, right? But even doing that doesn't help at all. It's still pretty bad. So a lot of times it's better just not to put copper in between here at all and just have no copper. Like you can have it underneath for a ground reference plane, but not like copper on the same plane. We can talk more about that too if you have any questions, right? It should be covered in those additional videos too, right? But now we can basically run the design rule check again, right? Report polygons and do that. And now we have one warning: design contains shelved. So it just told me that, hey, what are you doing? There's a shelved polygon that you didn't unshelve, right? That I basically had for the demonstration. And I just need to go to polygon forms and then just like go to here. And then unshelving, I just select A, Control A, and then shelving, unshelved, select all. And you can do pretty much report, first report all polygons, and then apply OK. Oh. Alright, I keep making oopsies on that where it doesn't actually go through, but you can just right click and report all, and then now that's good. So now if I run the design rule check, we should be all good, no errors. But it is fine to have errors sometimes. There's some things that you can risk or like aren't really important, like if you have these two silk screens right next to each other where they're touching, it'll give you an error, but like in reality it doesn't really matter if they're touching, it just might make it a little bit more confusing. Right, and then now the next thing you want to do is get ready for fabrication output, but I'm going to pause this video and then we can continue on for the next one. Okay, we're now back in business. So now we want to get ready for designing the PCB. So one thing you want to do now is just when you're in here and you have the project ready, you just make sure that the project is saved. We'll save the project, right? You want to get ready for, you have to be also inside the PCB document. We want to get ready for exporting fabrication outputs, right? And this Gerber files, which doesn't include the drill files, I like Gerber X2 because it includes that for you, makes life easier. The default is honestly, you can just choose that. It basically gives you everything you need. Right, the only thing I'd maybe do is that, see, you have the Gerber board profile too. So in older programs, you won't have that. So you just have the mechanical layer one that you have to go off of. And a lot of CAM operators will be able to figure that out. And you'll know what I mean later when I talk about CAM operations, as well as you have the units and how like this basically will display the CAM and whatnot. So you just apply that. Right. And now we have pretty much the CAM. This is basically what the CAM operator sees. You can come over here down to the settings. You go to Camtastic, and now you're able to turn on and off settings. And it's basically there's going to be some discretization, right? You're going to lose quality, or pretty much just the more specific term is quantization. Right? You're going to lose resolution. So really funky geometry or really tiny, like complex geometry is going to be like smoothed out pretty much. So it's like all the edges get low passed pretty much, right? And what you want to do now is that you just basically export and then Gerber. Right, and then you just keep the default settings. You can do OK. And now, actually, there's one thing I believe you can do too from here. is that you can also do more settings. So it's decimals. So you can choose 5 for more accuracy, and then this doesn't really matter, but you can do, I would recommend 5 usually. I'm just gonna keep it 4. So hopefully, this is a very simple board. And now I just want to make sure that I select the file here. And then what you can do now, I believe sometimes OBS might fight me on the GLC upload. But this is how I was able to make the PCB for the new NRF chip, right? And what you can do now is that you just pretty much, did I accidentally, here, let me redo that again. There's some that are marked today, and there's this stuff from yesterday. So delete that. We do now select all of them. And then you just compress to zip file. And then now we have a zip file. And now we do order now. Right? And we basically just slap this guy in there. Hopefully the upload doesn't have a problem. Yesterday there was problems, but today hopefully it doesn't mess with us. But I think there's something that happens when I have OBS running, because it just kind of like fights me on that part. But usually that'll be the whole gist. It'll auto select all these. So usually you'd be like 4 layers, 5 is the minimum quantity, and it'll basically auto select based off the schematics of the PCB, right? And then you have like different designs. You can choose the default thickness, right? Reduce 1 ounce copper, right? We can go over this together when you order your first PCB. And then there's also impedance matching too. That's also an option here. And so you can specify stack up, right? And you can confirm, you can choose the one that we did, which is just this one, 7628, right? And that'd be pretty much all the steps. This guy's going to keep loading indefinitely, but pretty much that's what you do to get your PCB printed, and then you just order it. I do bulk ordering just because there is like shipping costs, because it does come from Asia, right? And there's coupons too, so you have more flexibility on that. And then now you want to go back to the PCB here, and then you get a bill of materials, and you can pretty much, I believe you can customize these a lot more to make it easier for you, right? You can set up different templates. Right, but basically we can do sometimes too is that you have the component names right here in the comments, and what you can do, like that's why sometimes you want to make the component name be the comment, so that you can use that as a way to pick up the items at the store, right? And there's other ways you can set this up too to make it easier for you, right? And now you can go to JLC PCB, you can go to your accounts. Oh, thank you. So view carts. Right. Oh wait, I'm gonna export that. I forgot where I exported that. So pretty much, let's just go down the downloads and we'll just say like new PCB project. Right. And now I click OK. We don't need to look at my Microsoft account. And then now, all right, we'll now go over here. Right, and we can just delete what I had here previously because it's not important. And now you can go here, you can put the BOM here, and we can choose, that might be mapped back to your part number. This can be select, this can be select. The quantity, here's quantity, right? And then it'll try its best to look what we have in the cart and add whatever we can. And unfortunately, sometimes it doesn't come up. We have the one component here, right? And it's because it's like some of these just aren't like covered for, say, right? Like, this will be like the, right here, it might be just the 13 that's causing issues, and the minus, right? We can try looking up there. And now we have something else, but you can tell here that that's good. This is good. This is the good size, right? So this would be good. So we can just basically add that. And the one thing about adding carts is you have to look at the cost per price, right? Because it's actually a lot cheaper to order 10 than like a very few amount, because the unit price drops by like 1/3 when you order 10, right? So sometimes you want to take advantage of that. Like if you look how cheap it is if you buy 100, right? So you're like, oh, okay, for really like components that use a lot, like 1 microfarad or 0.1 microfarad, it might be good to order a lot of them. So you always have the size on hand, and if you use 0603 or 0402 for all your boards, you'll have a lot of selection moving forward that you can test and play around with. Right, and that's kind of the unfortunate of that, is that you have to do a lot of work to set up your BOM, so it's able to go 1-to-1 with these. Right, so it works. So that's the one thing that's unfortunate, but yeah, we got one thing. That's better than nothing, you know? And we can do too is just like a lot of the work that you do, the prep, and then you can like also look into how other people prep will make things a lot easier for you. But this makes it a way for you to be able to kind of like, so you don't have to click on all the components and see which each one is. You're able to get like kind of a list of what you had from your Excel sheet here. And you're able to pretty much get an idea of like what you want to add. Because if you copy this and you just put this online, right, you're going to get like a very similar component, and then that's when you can add it. As well as you want to make sure that the language here, right, you want to make sure that you're ordering the Canadian flag doesn't always mean like if you go digitkey.ca, this is language, right? Like this is just the Canadian web front. But if you choose USD, which is always like auto selected to, you will pay import fees, right? This is international trade borders. You want to choose Canadian and update. And then that's how you do that, and that's all good to go. But fortunately, this thing fights me when OBS is open, but I'll make sure that we're able to do it together going forward, just to as you do the first PCB order, right? To make sure we choose all the right options. It's cool to choose different colors, but it adds a few more days. But, you know, sometimes if you want to be really happy about what you make, just choose what makes you happy, right? But that's pretty much the whole shebang on Altium 365 and any additional features that you might want to learn on top of what you had in the tutorial.